I would like to discuss the different modes of operation of a BJT, primarily focusing on its switching characteristics and how it really works in regards to its construction. This is the symbol of an NPN BJT. This terminal is the collector, this one is the base, and this one is the emitter. The collector is a large region consisting of N-type material, and the base is a thin region of p-type material, and the emitter is a moderately sized region with heavily doped N+ material, and hence the emitter consists of a large amount of free electrons. The collector consists of moderate amount of free electrons, and the base consists of a very small number of free holes. The BGT is mainly expected to carry the load current from its collector to the emitter, and the base is used to control the amount of current that flows through it. The BGT can be used as an amplifier and also as an electronic switch. To understand that, first let's see how a mechanical switch works. Suppose this is the supply and this is the load. This could be an LED, this could be a motor, or maybe just a resistor. And the circuit is interrupted by a mechanical switch. If we push the switch, the current will flow from the supply to the load to the ground, and the load will work. The switch is on. But if we do not push the switch and let it be, then the current cannot flow. This switch works with a mechanical input, that is using a force. But for electronic control of switches, we can use components such as the BGT. The BGT can be put instead of the mechanical switch, where the current is expected to go from the collector to the emitter. We'll control this switch by means of the base current. If there is no base current, then no current will flow. But if there is adequate amount of base current, then you will get current flowing from the collector to the emitter. Now in this simulation, you can see there is current flowing into the base, and as a result, the collector to emitter will act as a closed switch and the LED will turn on. But if the base current is zero, then the BGT is turned off. Now, how does it really work? For the load to work, current must flow from the collector to the emitter. However, there is this discontinuity introduced by the base layer. The base layer consists of holes that can facilitate the flow of electrons from the collector to the emitter. But there are not many holes in this lightly doped region, and hence not much current can flow from the collector to the emitter. So the BGT, when there is no base current, actually acts like an open circuit. Now, if we introduce holes into the base region by means of a base current, these introduced holes will allow more current to flow from the collector to the emitter. Actually, the number of holes introduced per second into the base region determines the number of electrons that can flow from the collector to the emitter. This is actually given by the equation IC max is equal to beta IB, where beta is the current gain constant of the BGT used. So if the base current is 0 milliampere, the maximum amount of collector current that the BGT can carry is 0 milliampere, which means the BGT cannot carry any current. Then the collector to emitter voltage drop is equal to supply voltage. However, if the base current is 0.1 milliampere, and let's say the BGT has a current gain constant of 100, then the maximum amount of collector current that can be carried by the BJT is 10 milliampere. If the VCC is 5 volt and the resistance is 1 kilo ohm, then the load current required is 5 divided by 1K, 5 milliampere. And this 5 milliampere is well within the maximum current limit of 10 milliampere. So 5 milliampere current will flow from the collector to the emitter, and the BJT can be considered as a short circuit like a closed switch. And the voltage drop across the BJT like a good switch is very low, which is about 0.3 volts. With 0.3 volt drop across the collector to emitter, the collector current will actually be 4.7 milliamperes by using KVL, but that's not much of a problem. However, what will happen if we increase the supply voltage to 15 volts? In that case, the current requirement will be equal to 15 milliampere. However, the maximum current capability is 10 milliampere. So the current that can flow through the collector, that will flow through the collector, will be 10 milliampere, which means there will be a 10 milli into 1K 10-volt drop across the resistor, and the rest of the 5 volts will drop across the BJT. If we increase the supply voltage further, the current will slightly increase, but the voltage drop across the BJT will keep on increasing. You can consider the BJT as a variable resistor whose resistance increases to ensure the current across the BJT stays according to the maximum current capability. So if you increase the supply voltage to, let's say, 16 volts, the current will stay fairly at 10 milliampere. It will increase slightly, and the voltage drop will increase to 6 volts. And if we increase further to 20 volts, it will increase to 10 volts with only a slight increase in the collector current. These three different stages are the three different modes of operation of the BJT. If we see the internal construction of the BJT, there are two PN junctions over here. The first PN junction is the base to collector junction, and then the second one is the base to emitter junction. During the cutoff mode, there is almost no voltage or current in the base. As a result, both of these junctions are reverse biased. This leads to the BJT being in the cutoff mode where it acts as an open switch. Next, when we provide adequate base current into the BJT, the voltage drop across the base emitter junction will be 0.7 volt, and the voltage drop across the collector emitter junction will be 0.3 volt. If we do a nodal analysis, you can see the emitter is grounded, so the emitter will have 0 volt. The base to emitter voltage drop is 0.7, so the base voltage is 0.7 volt, and the collector potential is at 0.3 volt, since VCE is 0.3 volt. So we can see the base is at a higher potential compared to both the emitter and the collector. So both of these junctions are forward biased, and this is the saturation mode of the BJT, where both junctions are forward biased and the BJT acts like a closed switch. But when the base current is not sufficient enough, the collector current will be limited to a value equal to beta IB, and there will be a large voltage drop across the collector to emitter terminals, which let's say in this case was 5 volts, and the base to emitter voltage will be 0.7 volts. So if the emitter is grounded by nodal analysis, The potential at the base terminal will be zero point 0.7 volt and the potential at the collector terminal will be 5 volts, which means the base to emitter, although is forward bias, the base to collector junction is reverse bias. This leads to the active mode of operation of the BGT, where it sort of acts like a variable resistor that always tries to ensure that the maximum current limit is not crossed and will have a voltage drop across it accordingly.